So this video will cover section 6.1, energy diagrams. So for a reaction to occur, two molecules must collide with enough kinetic energy to break bonds. So here we have a generic chemical equation with a compound AB plus an element C, and the reaction needs to break the bond between A and B, and then create a new bond between B and C. And so for the reaction to occur, you need the B and C to collide, and they need to collide with enough kinetic energy to break the bond of A and B, A, B together. And so the orientation of the molecules must be correct as well, because if the molecule AB hits the atom C on the B side, then you will have a proper orientation and C will collide with B, and then a new bond can form between B and C. But if, for example, C collides with A, then you have an improper orientation, and then C will collide with A, and no new bond between B and C can form. So the orientation is also important. So the energy diagrams are some diagrams that we draw to represent what happens during the reaction, and it shows what happens in terms of energy. So the x-axis represents the reaction coordinates, which you can see that as time passes. So we start with reactant on the left and end up with product on the right. And so reactant and product are positioned at different energy levels. So on the y-axis, it's the energy going up. And so in this case, here the product are assumed to be lower in energy than the reactant. So their level of energy has been drawn at a lower level of energy than the reactant. And so this represents how our previous molecule AB plus C. So these are the reactant. They are at a higher energy. And so the blue line here shows how we need to get some energy to go into the transition state. And the transition state is an intermediate state where there is no more the AB molecule and there is not yet the BC molecule. It's kind of in between. It's like dashed between all of them. It's half broken bonds and partly formed bonds, right? And so to be into that transition state, you need energy, because the potential energy of the reactant increases as bond breaks, right? Atoms are more stable when they are bonded, and so when you break bonds, this increases the potential energy of atoms. And then when the new bond can be formed between B and C, the potential energy decreases again as the bond is being formed. And here, because the products are lower in energy, you will end up with a lower energy than you started with. And so notice how the difference in energy between the transition state and the reactant level of energy is called EA. Capital E subscript A is the energy of activation. It's the difference in energy between the reactant and the transition state. It can be thought of as the energy barrier that must be overcome for the reaction to occur. Right, for this reaction to occur, the reactant will have to get that amount of energy, to go past the transition state. So EA, the energy of activation, is the minimum amount of energy that the reactant must possess for a reaction to occur. So E of A is called the energy barrier, and the height of the barrier determines the reaction rate. So reaction rate here, you want to think about the speed. And so when you have an energy of activation that is very high or high, Very few molecules will have enough energy to cross the energy barrier. And so the reaction will be slow because few molecules will have that amount of energy. And then at a time, only a few molecules will be able to react. So you will have a reaction, but it will take more time. It will be a slow reaction. Now, when the energy of activation is low, many molecules will have enough energy to cross the energy barrier, and then the reaction is fast. So more molecules at a time will have the energy necessary to go into that transition state and be changed into product. So you will have a faster reaction rate. The difference in energy between the reactant and the product is the delta H. The delta H we have learned is the enthalpy change or the heat of reaction. And so an enthalpy change is then the change between the enthalpy of the product and the enthalpy of the reactant. So you can see delta H can be written as enthalpy of product minus enthalpy of reactant. And so on the left side here, we have the energy diagram of an exothermic reaction. Exothermic because we see that the delta H, when you do enthalpy of product minus enthalpy of reactant, it's a negative value. And that happens when the product are lower in energy than the reactant. And usually the energy barrier is also smaller for an exothermic reaction, but not necessarily. So here it shows a low energy barrier. So there should be enough molecules that have the energy to go into the transition state and then become products. So remember how delta H, when it is negative, it's an exothermic reaction. And now when the delta H is positive, the reaction is endothermic. And so we see with the energy diagram here that for an endothermic reaction, you need to have product with a higher enthalpy than the reactant. Because if you do enthalpy of product minus enthalpy of reactant, it's going to be a positive difference. And so that represents an endothermic reaction. Because when you have the reactant being lower in energy than the product, then you will need to provide the difference in energy between the two for the reaction to occur. And so that's an endothermic reaction. And usually endothermic reactions tend to have a larger energy barrier. Energy of activation, EA, tends to be greater as well.